All right, I guess we'll go ahead. So last time, or the last time we had class, we were talking about the harmonic oscillator in one dimension. For which the Hamiltonian is the momentum operator squared over twice the mass plus 1/2 m times an angular frequency squared times the position operator squared. And so a couple of comments on this. One is this commutes with the parity operator. And so according to our general facts about the parity operator, there are common eigenvectors of the energy eigenstates and the parity. So we should find all stationary states to be parity eigenstates. And the other thing that we did at the very end of our last class meeting is we proved that the energy eigenvalues must be positive. So we will find that useful later. And so we're going to do 3 approaches to the harmonic oscillator in one dimension. The first, and this is the order in which we will do them. The first is the position representation approach. And this is the hardest one, but it has several advantages. The first is that it will build character. And the second is that the method that we will use, although it's harder, it applies to many other problems. So that's an advantage. It's more versatile. The second approach is the momentum representation approach. And this has the advantage that once we do the position representation approach, this will require no extra work at all. We will just be able to adapt the results we had for position representation directly to get the momentum representation. And then finally, we'll do it the easy way, which is the energy representation. So this is not only easier, but it's more useful. So you could say, why don't we just do the easier, more useful way first? And the answer is because it's really special to the harmonic oscillator problem. And so it won't apply to more complicated situations. Okay. All right, so let's go ahead with the position representation approach. In the position representation, that means we're going to write things by taking an inner product with a bra on the left, x, of the equation we want to solve, which is the Hamiltonian, p squared over 2m, plus 1/2 m omega squared x squared, times the energy eigenstate we want is equal to the energy eigenvalue times x psi. Okay, and x psi is by definition the wave function. Okay, and in the position representation, we can take how p and x are represented and plug that in. And so this becomes minus h bar squared over 2m, 2 x derivatives, plus 1/2 m omega squared x squared the number times psi of x. Okay, so notice we've changed the x squared the operator into x squared the number. We've changed p squared the operator into minus h bar squared 2 derivatives with respect to the number x squared. And that's all because now we're acting on wave functions rather than kits. That's what it means to go to the position representation. And so we can rewrite this slightly by just dividing through by minus h bar squared over 2m, just to make it a second order differential equation with the coefficient of 1 in front of the second derivative. And so what's left here is 2m over h bar squared. We're also going to move the e to the other side of the equation. And so it's e minus 1/2 m omega squared x squared times psi. That equals 0. Okay, so that's the differential equation we want to solve. And there's a very useful trick that applies to very generally to this sort of problem. And that is, if possible, you want to use dimensionless variables. So it's going to be convenient. For convenience, we're going to define our original number x to be b times y, where b is going to be a constant length that I'm going to tell you what it is in a minute. And y is our new variable, and it's dimensionless. So we know x has units of length, and so if b has units of length, then y is dimensionless. And so now we need to be able to take derivatives with respect to x, but that's just d by dx is equal to 1 over b d by dy. Okay, so again, I haven't told you what b is yet, but we'll figure it out in a minute. Yeah, so meanwhile, we plug that change of variables into the differential equation. And we get second derivative of psi with respect to y plus 2me over h bar squared times b squared minus m squared omega squared b to the 4th over h bar squared times y squared. All of that acting on psi has to be 0. So now psi is a function of y. Okay, but that also makes it a function of x, of course. Okay, now is where we get to choose b, and we want to choose b to make things as simple as possible. So what we're going to do is we're going to choose b to make this be equal to 1. Okay, and so that implies let's choose, first of all, that b is going to be the square root of h bar over m omega. That's something with units of length, which you can check by plugging in the units of h bar and omega. Omega has units of 1 over time and the mass. And so this is indeed a length scale. And it's a length scale characteristic of the particular harmonic oscillator we're talking about. Okay, and we're also going to want to make this term nice. And so let's call this term 2 times curly e. And so curly e is related to regular e by e equals h bar omega curly e. So curly e is also dimensionless. And so this is just the fact that it's often a very good idea to change variables to make everything dimensionless. It'll just reduce the clutter. And in fact, in this case now, the differential equation looks like 2 derivatives of psi plus 2 times curly e minus y squared times psi equals 0. Okay, so we've gotten rid of all the dimensionful quantities. We just have this differential equation to solve. Okay, the 2 is left there just here, just for, it turns out it's a little bit more convenient to leave it there. And of course, we can't get rid of curly e because we're solving an eigenvalue problem And so we want to be able to solve for the eigenvalue, which is E. And so we have to have something that is this, which is there to be solved for. Okay, so we are going to now solve for psi of y and the eigenvalue curly E. And when we get curly E, we'll go back to this equation and get the actual energy eigenvalue. Okay, so to solve this, let's first take an extreme case. That's another strategy that's very useful in solving problems. When you don't know what else to do, consider a simpler, more extreme case. And so let's consider the case of large y. In fact, large absolute value of y, because large positive y and large negative y are going to behave the same. Okay, so now just rewriting, let's even rewrite it more compactly by using prime for a derivative. So the equation just becomes psi double prime is approximately equal to y squared times psi. So what did we do there? We said for large y, this term right here, oops, this term right here is much more important than that term because that term's a constant. If it's not much more important, we should just look at larger y until this term is more important. Okay, and so that's why we neglected the curly E term here, which makes things even simpler. And so now we can solve this equation by making a guess. Let's guess psi is approximately some constant times a power of y times an exponential of y squared. Of course, knowing what guess to try is something that you either have to be lucky or you have to have some insight into the problem already, but I already know the answer, and so that's why I'm making this guess. I already know that it's going to work. That's really the way all differential equations are solved the first time anybody solves them. They stare at it, they make some sort of guess, and then once you've made the guess, then of course it's much easier to justify after you've already got the answer. Okay, so now if we make this try, now we can compute psi double prime. First, let's compute psi prime. Okay, and so there's the constant out front. And then we're going to use the product rule. So there's a term n y to the n minus 1 from taking the derivative of y to the n times e to the alpha y squared. And then there's the contribution where we're taking the derivative of e to the alpha y squared. So that's y to the n 2 alpha y times e to the alpha y squared. Okay, now we can again use the fact that we're only thinking about large y right now because this term has 2 more powers of y than this term does. And so we can neglect the first one. Neglect for large y. So this is approximately 2 alpha y times the original psi. Okay, now we're going to take another derivative because from here, what we need is psi double prime. So psi double prime is, well, we saw what happened when we took one derivative just multiplied by 2 alpha y. And so when we repeat that, the same thing is going to happen. We're going to get another factor of 2 alpha y. So it's 2 alpha y squared times psi. Okay, plus contributions that have fewer powers of y, and therefore we can neglect them. Okay, now if we look at this equation is going to be true if alpha is equal to 1/2 or minus 1/2. Right, and that's from comparing with this equation. This has the same form. It's just got a 2 alpha quantity squared in front of it. And so either alpha equals 1/2 or minus 1/2 will solve it. Okay, and so what we conclude is for large Y, the wave function behaves like one of the two things, a y to the n, e to the y squared over 2, or a y to the n, e to the minus y squared over 2. This is the first one is the plus 1/2 for alpha, and the second one's the minus 1/2. But now we can neglect the first, we can reject the first one. And the reason we can reject it is because it's not normalizable. Okay, this wave function is growing exponentially for large Y, which means it's growing exponentially for large X. And so even if we do a trick like say, well, let's put this in a box that's very large, it's going to be, this solution is going to be much larger. If we put it in a box with the size of the galaxy, it will be much larger everywhere else except where we are. And so this is not a reasonable, physically reasonable solution. Okay, so that's telling us that the second option, the alpha equals minus 1/2 option, is going to be working as long as n is some fixed number. Okay, so what we've learned is that the wave function is going to behave like e to the minus y squared over 2. And so now with that knowledge, let's go back to the general problem of any y, not just large y. And we're going to try a solution that looks like some coefficient function multiplied by the exponential that we just found works for large y. So as long as u of y is not some exponential, this will have the same properties as the solution we found for large y. And so in particular, we can try u of y is just a sum of powers of y. So let's do that. Sum j equals 0 to infinity. C sub j, y to the j power. Okay, now, a couple of things about this. You could say, well, how did I know that it was going to be a sum of powers of y and not, say, cosine of y or sine of y or something like that? And the answer is we're just guessing at this point. And the justification is going to be, does it work or does it not work? That's really all it is. Okay, but we also made an assumption here that there are no negative j's. And that at least we can explain why we made that choice. That's so that the wave function doesn't blow up, or so that it's finite as y goes to 0, which is another extreme limit. Okay, so that psi of y will be finite as y goes to 0. All right, so the point there is there's nothing really weird or special at y equals 0, which is the same thing as x equals 0. That's not a particularly special point. And so there's no reason why the wave function should blow up there at all. Okay, so now we're going to plug that into the differential equation. We've made a guess. We're going to plug into the differential equation. Okay, and so you plug that in, and after a little bit of algebra, which is not too bad, you get the following. You get a sum from j equals 0 to infinity, c sub j. And now from taking the two y derivatives, the double prime, you get j times j minus 1 times y to the j minus 2 plus 2 times our curly e minus 1 minus 2j, all times y to the j. Okay, and that whole thing has to equal 0. So I should make a note here. There's a little bit of work omitted, but you can all take derivatives using the product rule, so that's not too hard to check. Okay, and so now we have to, now the idea is to solve for the coefficients C sub j. If we find a solution, which by the way is not really guaranteed, but if we do find a solution, then that'll be a good solution. And if we don't, we would have to try something else. But again, I happen to know the answer in advance, so I know this is going to work. All right, and to show that it works, it's nice to use a little trick here. So if we look at the first part of this, we notice that this vanishes for j equals 0 and j equals 1. And so we're going to rewrite it, taking advantage of that. Okay, and so the first thing we're going to do to rewrite it is just write it as some j equals 2 to infinity of the same thing. We haven't done anything yet because the j equals 0 and j equals 1 terms vanished anyway. But now we're going to make a relabeling. So we're going to let j in this equation be m plus 2. And that way this becomes some m equals 0 to infinity. Because if j equals 2, m equals 0, of c sub m plus 2 times m plus 2 times m plus 1 y to the m. Okay, and now having done that, we're going to turn around and rename m as j. It's something we're summing over anyway, and so we can call the thing that we're summing over anything we want. Instead of calling it m, we're gonna rename it back to j. And so that first term is equal to sum j equals 0 to infinity, cj plus 2, j plus 2, j plus 1, y to the j. Okay, and the advantage of doing these little tricks is that now if we stare at the two terms, there's a term with y to the j. And now we've successfully turned this term with y to the j minus 2. So it also is proportional to y to the j. And that means we're going to be able to pull out a common factor of y to the j. Okay, so that's the trick. And so our equation becomes sum j equals 0 to infinity. Both sums also, by the way, start at j equals 0. That term did, and for this thing, that also depended on j equals 0. So that's nice. Okay, so this is sum j equals 0 to infinity of y to the j times c sub j plus 2, j plus 2, j plus 1, plus c sub j, 2 epsilon minus 1 minus 2j. All of that is supposed to equal 0 if we're going to solve our differential equation. Now, the big advantage of having a common factor of y to the j is because if we say, well, y can be anything, for this whole equation to be 0, it must be true that each power of y vanishes independently because they're each independent. Okay, so the argument is each y to the j is an independent number. And so for the full thing to be 0, we can just look at them one at a time. So look at each j on its own. And so for this to equal 0, this whole stuff right here has to equal 0. Okay, and so then we can solve for c sub j plus 2. Namely, it's 2j plus 1 minus curly e over j plus 2 times j plus 1 times c sub j. So the great thing about that is that tells us, let's say we know c sub j, then we automatically know c sub j plus 2. And so if C0 is known, if we know the very first coefficient, then so are C2, because you plug in j equals 0. And then once you know C2, you know C4. And once you know C4, you know C6 and C8, and you know them all. Okay, and if C1 is known, then so are C3 and all the odd ones, C7 and C9, etc. So that means all coefficients are actually known in terms of just two coefficients, C0 and C1. If we know them, we know everything. Okay, so all coefficients known in terms of C0 and C1. And not only that, but having done so, we will have automatically solved the differential equation. So it indeed does work. Our lucky guess of what to try for this function u of y does work. And so we can even write down the solution for u of y. There's one part that's proportional to C0, and it's 1 plus the part that we were calling C2, which is now, by plugging into here, we now know that that's 1 minus 2 epsilon over 2. And I see that I dropped a factor of 2 right here. That should have been there. Okay, times y squared. And then there's the y to the 4th term, which is like C4, which is going to be 1 minus 2 curly e over 1 times 2 times 5 minus 2 curly e over 3 times 4. That's times y squared, or y to the 4th. And then we can keep going. We'll get a y to the 6th term, a y to the 8th term, etc. Okay, and then there's C1 times y to the 1st power. That's the original C1 term. And then there's the C3 term, which is 3 minus 2 epsilon over 2 times 3 times y cubed. And then there's the y to the 5th term, which looks like 3 minus 2 epsilon. We're just plugging in the results for each of our coefficients as we get them. That's y to the 5th, and then there will be y to the 7th, etc. Okay, so that's our general solution for u sub y. That we then, once we've got this u sub y, as a reminder, what we're supposed to do with it is we're supposed to go way back up here and plug it in to get the wave function for psi. And then once we've got the wave function for psi, we can even go back and plug in what y is from this equation, where b was given by this. Okay, so that's looking back at where we've come. Now this is an infinite series, or so it would appear. because for each coefficient, then the next one with a higher power of y will follow from it. And so it apparently contains all powers of y and not just fixed y to the n. Now, it turns out that's not going to work. And one of the reasons it's not going to work is when we looked at what happened for large y, what we found is that it wasn't all powers of y times the exponential. It was, in fact, some fixed power of y. So we'd like to understand this discrepancy of why we're now getting all powers of y. Okay, so to understand that, what we want to do is we want to look at what happens for very large j. That is large powers of y. So for very large j, our equation for the coefficient boils down to Cj plus 2 is approximately 2 over j times C sub j. Right? That comes from this equation, where for large j, we get to forget the plus 2 and the plus 1 and that plus 1 and the minus 2e. We can throw those all away because they're small compared to large j. Okay, and so that's where this came from. And so now let's consider the function that we're going to get if we just include that part of the C sub j. So consider the function y to the n e to the y squared. Okay, this has a series expansion that looks like the following. Sum k equals 0 to infinity, y to the n, y squared to the k over k factorial. I've just plugged in the definition of e to the y squared. So this is just rewriting it. Sum k equals 0 to infinity of y to the 2k plus n over k factorial. Okay, and so now we can let j equals 2k plus n. There's a lot of tricks of relabeling indices today. Okay, and so then this is equal to sum over j of y to the jth power over j minus n over 2 factorial. J minus n over 2 happens to be an integer. Okay, and so this is sum over j cj prime y to the j for j equals n, n plus 2, n plus 4, etc. Those are the allowed values of j, where this cj prime is 1 over j minus n over 2 factorial. Okay, so we're just looking at this function just to see how it compares to the function we've got that we solved for. And so we notice that they have very similar coefficients. In fact, cj plus 2 prime is 1 over j plus 2 minus m all over 2 times cj prime, which is approximately 2 over j times cj prime. Okay, and now the key thing is to notice this recurrence relation for these coefficients is the same as the one we actually found. And so that allows us to conclude that u of y is, the u of y that we found is y to some power, n, times e to the y squared for large y. So now let's plug that u of y to get the wave function. psi of y is approximately, I should make approximates for all of these, I guess. Psi of y is approximately y to the m e y squared times e to the minus y squared over 2, which is approximately y to the m. I guess I should call it n. I've been calling it n here. Okay, so this is y to the n e to the y squared over 2. And indeed, we had found that we had solutions of that form, but these are exactly the bad solutions that we've already neglected, already said couldn't be there. So it looks like we did all this work of solving the recursion relation for these coefficients, and all that we got was a solution that we had argued before was a bad solution and we shouldn't use it. Except there's one way out, and the one way out is what happens if you get to some value of the coefficient and it turns out the coefficient vanishes. If the coefficient vanishes, then all the higher powers of coefficient will also vanish, and then you cannot have a function that grows exponentially, and everything will be okay again. Okay, so that's the conclusion. The only way out to get a real solution that makes physical sense is that the series that we found for u of y is not actually an infinite series, but it must terminate. And when we do other problems, for example, the hydrogen atom, we're going to find exactly the same thing is going to happen over and over again. This is a very common theme, that you write down what looks like an infinite series solution. You find out that if it really is an infinite series solution, then it can't work for one reason or another. Therefore, it can't be an infinite series, and it must terminate and actually be a polynomial. And so that's what's going to happen here. Okay, so to realize this dream of the series terminating, it must be true that some coefficient for some integer j is equal to 0. Then all larger j's, so cj plus 2, cj plus 4, all those coefficients will just vanish also. Okay, so that's what we need to have happen in order to have a solution that works. So let's go back to our original relation for the cj plus 2 and the cj. And where was that? It was way back up here. Okay, so that's a super important equation. I should have probably highlighted that, because that's the key to the whole thing, is that what we want to do is apply this equation in such a way that Cj is, so that one of the coefficients is going to vanish. So for that to work, it must be true that the numerator here vanishes. That's what will make the next coefficient in the chain vanish. And so we need this to vanish for some integer j, which we're now going to call n. Okay, and so what we need is we need 2n plus 1 minus curly e to equal 0 for some n. Okay, that's what will make the series terminate, and we won't get the bad solutions. We can have something that has a chance of being a good solution.
Isn't it minus 2 curly?
Yeah.
Minus 2.
Is it minus 2 curly? Yeah.
Very good. Yes, thank you. Okay, and so now the allowed, I'm dropping my 2's. And so now the allowed curly e's are n plus 1/2 for integers n equals 0, 1, 2, etc. And now translating the curly e back into the regular E, that's just multiplying by h bar times omega. And now I'm going to put the label n on it, because of course it depends on n. So it's h bar omega times n plus 1/2. Okay, and by the way, the n here is not only telling us which energy eigenvalue we have, it's also the highest power of n, or sorry, of y in our expression for u of y, which is now a polynomial, not an infinite series. Okay, so in fact, these polynomials have a nice name. U of y are known as the Hermite polynomials. And by just plugging in, we can figure out what they are. So we'll call them h. And then there's a subscript telling you what n is. So let's look at h0 first. That's a function of y. And that's where we just have the first coefficient is 1, and all the coefficients after that are 0. And we might as well choose that coefficient to be 1, because we're going to choose a normalization for the state kit anyway. And so we can just call this 1. Okay, h1 of y is where we choose c1 to be the non-zero one, and everything after that is 0. And so you might think we should choose c1 to be 1, but no, it turns out it's nicer if you choose it to be 2. So just by convention, h1 of y is 2y. At this point, the normalizations are sort of arbitrary anyway. And then if you do h2 of y, that's where you get c0 and c2 are both non-zero. And it turns out the standard normalization makes this equal to -2 plus 4y squared. h3 of y is, it turns out, -12y plus 8y cubed. h4 of y is 12 minus 48y squared plus 16y to the 4th. And h5, we know this is going to be a polynomial of order 5, and it's only going to have odd coefficients because it's going to be an eigenstate of parity. So it's always got either even or odd, but not both. And so this is 120y minus 160y cubed plus 32y to the 5th. And you can have your computer compute these as many of them as you want. As I just mentioned, they're all either even or odd, but not a mixture, polynomials. Okay, so there are many nice things you can prove about these polynomials. One is with the normalization that we've picked here, or actually more generally than that, the normalization is defined so that if you integrate from -infinity to infinity of one Hermite polynomial times another one, times a factor of e to the minus y squared, dy, that's equal to a Kronecker delta that says it's only non-zero if n and m are the same. And then there's a weird factor which turns out to be square root of pi 2 to the nth power times n factorial. Okay, and so this orthogonality is actually obvious. Well, obvious is a relative word, but it's obvious if one of n and m is even and the other is odd. So the reason it's obvious, in quotes, is because then when you do the integral, you find out if one of them's even and the other one's odd, then there's a contribution from -y that always cancels the contribution from +y. You're integrating an odd function over an even interval here. And so that's why it has to vanish. It's not so obvious what the rest of this coefficient is, but that's what you get. Okay, so finally we can put everything together and get the wave function. So what I'm going to do is I'm going to change y back into x. I'm going to label each stationary state wave function by the n that goes with it. And I'm going to work out from here, from this normalization condition, actually including the whole thing, I'm going to work out what the normalization in front of the whole thing is. And it turns out to be m omega over pi h bar 2 to the 2n, n factorial quantity squared, all to the 1/4, times the nth Hermite polynomial that you can get from our recursion relations. And then we can't forget the factor e to the minus y squared over 2. Okay, and so those are our stationary state wave functions, and these are orthonormal.
Dr. Martin, should the y's be x's? Or
No, so I'm using sort of a mixed notation here. I'm writing it as a function of x, okay? But when you see y on the right-hand side, you're supposed to translate the y still into x's. Okay, but the rest of the factors because they don't involve x or y, those I've evaluated here. So yeah. So I could, if I wanted, go ahead and plug in y in terms of x for both of these, but it would just make things messier. Okay, good. Other questions? All right, so that's it for today, except I wanted to mention that I handed back the midterms. Everybody should have got their midterm back. The scores were a little bit on the low side, but I would say not terribly so for the first exam. You're probably getting used to how I give exams, or you didn't know how I give exams. So now next time things might be easier. Also, somebody asked if I grade on a curve. I do grade on a curve. And so also you get to try homework. You get to try for the homework, which is on the web page today. You get to try redoing those problems as a means of making sure we understand how to do them. So I wanted to give a few hints. Sorry, I'm going to be running over a little bit late here, but these are hints for things that people had particular problems with, besides just arithmetic and things like that. So one is on part 1e, what you should find is that there's a degeneracy relevant there. The eigenvalues are degenerate. And so you're going to be using equations 3.1.3 and 3.1.7. Those are from the postulate section, with a sum over the degenerate eigenvalues of A. So in particular, you want to choose orthonormal eigenstates of A, alpha and rho alpha. The degeneracy happens to be 2, so you're going to be summing over 2 of them. Okay, problem 2. This is something that tripped up many people. So many people decided to use, and don't do this, decided to use the momentum representation in which the operator x is represented by the differential operator acting on psi tilde p's, I h bar d by dp. So in the momentum representation. So why shouldn't you do that? The reason is because the psi tilde p that you were given is not differentiable. And specifically, it's not differentiable at p equals 0 because it had different expressions for p less than 0 and p greater than 0. So here's the problem. Because it's not differentiable, if you try to do an integral where you're plugging in this relation, the derivative is just not going to work. It's going to blow up when you plug that in. So what should you do instead? So that's why part B was there. So instead, use the position representation from part B. One clue that that would be the sensible thing to do is because, well, you've got the position representation, and in the position representation, the operator x is just represented by the number x. And multiplying by a number is much, much easier than taking derivatives, especially when you have to take two of them, which is what you would have to do in the momentum representation. Okay, on a hint for part 2D. So 2D is said, assume that this particle is moving without a potential, which means the energy is p squared over 2m classically, or the Hamiltonian is the operator p squared over 2m. And so an easy way to get the probability that the energy is greater than some value E0 is you can write it as the probability that the absolute value of the momentum is larger than something that's very easy to work out. I'll just write question mark there. And then that's easy to evaluate if you use the momentum wave function. Okay, and again, you didn't have to actually work this out. You could just write it as an integral. But the idea is the integral is going to be an integral over p. That's the easiest way to do it. You can also do it as an integral over e. That's also not too hard. And then finally, a hint on 2e is you should be using the time independent Schrodinger equation. Okay, and that will allow you to solve for v of x as the problem asks. Okay, and so when you do homework set 6, which is due a week from today, those are the first two problems, is to redo these. And the standard homework rules now apply, so you can consult with each other. If my hints don't make any sense to you, or you just don't understand what to do, you can always send me email or ask for a Zoom meeting or anything like that. All right.
Will you be posting the midterm? Will you be replacing the Rickroll with the midterm? Because I just checked the site and it's not there.
Yeah, I can put that up. I thought I emailed everybody a copy of it, but maybe I didn't. I'll put it up there in any case.
Okay, thank you.
Sure. And then when I scanned in a couple of your papers, if you were using really thin paper, it turns out the scanners on the copy machines on campus tried to shred them. So I think I got everybody's midterms correctly scanned in, but you should check anyway. All right. And I'm actually, if anybody knows how to get Zoom, an easy way to get Zoom to automatically admit people now, I could use a clue because I tried to figure it out and I couldn't get it. So in any case, I will see you next. I'll see you on Friday if there are no further questions. And hopefully by then we'll have figured out how to admit you without having to go through that. I think you'll still need the passcode because I think they require that now. But how to get it automatically to admit you without me having to admit you by hand. All right, so I'm going to stop the recording now.